chat or your mic to answer these questions. The volume of dilute nitric acid that react with 25 cm cube of potassium hydroxide can be found by titration using the apparatus shown. Complete the box to name the apparatus. What we call this apparatus? So it is a burette. The next part, name a suitable indicator that could be used. So you can mention variety of indicators are there such as phenolphthalein, methyl orange, methyl red, phenolphthalein. You can mention any indicator, a suitable indicator. But normally for titration purpose, we do not use universal indicator as it shows a transition of the color at different pH. It has having different colors, which is difficult to recognize the color changes as color masking or transition of the color is there. That's why we use indicator which show only one change in the color. A student did the titration 4 times and recorded the following result. The titration numbers are given in the volume of dilute nitric acid. Which one of the results appear to be anomalous? So titration 2 result appear to be anomalous. And what could be a reason why, like in titration 2, a student added too much volume of the acid as compared to other? Yeah, that's a good. Did not close the tap. Even the indicators show a color change. A burette tap open accidentally. By increasing the aqueous potassium, or maybe greater amount of potassium hydroxide was used in the second experiment. Color change was not uh, observed quickly. Yeah, so maybe or overshoot or add too much at the end point. Use the other results to calculate an average volume of nitric acid that reacted with potassium. So the wrong result, random value will neglect and take an average. What will be the average of these three? 8.1, 18.1, 18.2 and 18.3 and divided by 3, that will be equal to 18.2 centimeter. The equation for the reaction taking place in a titration is shown. The student conclude that the aqueous potassium hydroxide was more concentrated than dilute nitric acid. Explain whether or not student conclusion was correct. Like as we know, 1 mole of HCl, 1 mole of HNO3 is reacting with 1 mole of potassium hydroxide. In a titration, what was the volume of potassium hydroxide? We use 25 cm3 of potassium hydroxide. And for titration, average volume of nitric acid from the burette, we need only 18.3. So for a complete reaction, 25 cm cube of potassium hydroxide only required 18.2 cm cube of nitric acid. Which solution is more concentrated? The ratio is 1 is to 1 between them. Like the number of the moles are same. And so student concluded that the aqueous potassium hydroxide is more concentrated. That is a student conclusion. Whether or not the student conclusion was correct, Is the student right? So student is wrong, and the reason is because smaller conclusion is incorrect, and reason for that is because smaller volume of nitric acid is needed, which shows it is more concentrated. As we know, the concentration is moles by volume. So wrong, as the volume of nitric acid is less than QH for a complete reaction. So it means when you compare the concentration, both require the same number of moles, but concentration is moles by volume. So if moles are constant, the one which is having a least volume, smaller volume, will have higher concentration. A student investigated the rate of a reaction between dilute hydrochloric acid and sodium thiosulfate. When dilute hydrochloric acid is reacting with sodium thiosulfate, what we'll observe, a sulfur, basically in this reaction it produces a sulfur, and when this sulfur is formed, the solution will turn cloudy. As the solution will turn cloudy, so we are not able to see what is under the flask, the text which is under the flask. So the text will disappear, and using this idea, if the text will disappear in a short time, we'll say the reaction is faster, and if it will take more time to disappear, it means the reaction is slower. So when these chemicals react, they form a precipitate which make the solution go cloudy. The formation of the precipitate can be used to find how fast the reaction proceeds. 5 experiments were done using the apparatus shown. 10 cm cube of dilute hydrochloric acid, 250 cm cube conical flask is there. This is a size like the maximum volume which the flask can hold, and so aqueous sodium thiosulfate is there. Experiment 1, a large imaging cylinder was used to pour 50 cm cube of sodium thiosulfate into a 250 cm cube conical flask. The conical flask was placed on a printed sheet of paper. 10 cm cube of hydrochloric acid was added to a conical flask. A timer started immediately and the mixture was swirled. Normally, when we want to swirl a mixture, we prefer to use a conical flask. Otherwise, if you have a beaker which is having a large surface area at the top, so the chance is there that the liquid might spill. That's why we use a conical flask. Time taken for a printed text to disappear, that is measured. Then second experiment, all the same things are done, but instead of 50 cm cube, we use 40 cm cube. Experiment 3, 35 cm cube. Experiment 4, 30 cm cube, and experiment 5, 10 cm cube. Record the volume of the distilled water. Why we add a distilled water? So that because if the total volume of a solution is same, then the concentration and volume of each component is directly proportional to each other. The one which is having a greater volume, the component which is having a greater volume, it means it is having more concentration. So record the volume of the distilled water used in the table. Use the stop clock diagram to record the results. So in the first experiment, 10 cm cube of hydrochloric acid and 50 cm cube of sodium thiosulfate is there. So what is the total volume of the solution? The total, in the first one we did not add a distilled water, as you can clearly see, it's not mentioned here. In the second experiment, we took 40 cm cube of thiosulfate, we had 10 cm cube of hydrochloric acid, and 10 cm cube of distilled water, so that the total volume of the solution will be 60. Here also 60. 35 cm cube of sodium thiosulfate, 15 cm cube of distilled water, then 20 cm cube of distilled water, then 40 cm cube of distilled water. Now you can use a screen annotation to complete this table. the volume of the distilled water in each experiment, and the time. So these are the time intervals and the volume of the thiosulfate, volume of distilled water. So 0, 10, the first one 0, 10, 15, 20, 40, and the time is 27, 33, 45, and this one is 66 actually, because it is 61 minute and then 6, so this will be 66. Rest all correct. Then from these results, draw a smooth line graph, volume of thiosulfate and the time it will take for the printed text to disappear. Volume of thiosulfate 50 and it was taking 27. So volume of thiosulfate was 50 and 27. When we plot this result, we'll have a, I'm just sketching a possible shape of the graph. So what we'll have this type of graph will be there. This will be the shape of the graph when you plot these results. As it shows that when the volume of thiosulfate decreases, because there are less particles, so it will take longer time for the formation of precipitate. From your graph, deduce the time for the printed word to disappear from view if experiment 2 was repeated using 20 cm cube of thiosulfate and 30 cm cube of distilled water. So because in the experiment 2 we were having 40 cm cube, so instead of 40 cm cube, if we use 20 cm cube of thiosulfate, so what you have to just the same using your graph, you have to show clearly. It will take a longer time, so on your graph you'll draw a line and find out accordingly, according to your graph. But keep in mind you have to show this working as it is mentioned here. From your graph, reduce the time and show clearly on your grid how you work out. So you have to draw the line, means the line for this, the original graph is there, and then draw a line from 20 and work out how much time it will take. The rate of the reaction can be calculated by using the equation shown. Rate is equals to 1 divided by time taken. Calculate the rate of a reaction using your answer to C1. So example, this was 135 seconds. Then we need a rate. So rate 1 over time. So 1 divided by 135, what will be the answer? 1 divided by 135. So 0.00741 and second inverse, because this is having no unit, or 7.41 exponent minus 3 you can also write, but second inverse. In which experiment 1 to 5 was the rate greatest? In which experiment the rate of the reaction? So experiment 1, and what could be the reason for that? Explain in terms of particle why the rate of the reaction was greatest in experiment 1. More particles are there, higher concentration of thiosulfate, so more collagen. More particles of thiosulfate, so greater number of successful collision that leads to faster rate of reaction. Give the name for more accurate piece of apparatus for measuring the volume than a measuring cylinder. Which apparatus can be used? So we can use a burette, and if it's 25 cm cube, you can mention a pipette as well. Suggest the effect on the result using a 100 cm cube conical flask instead of 250. Like we did the same thing. First we were having a 250 cm cube conical flask, but now the same solution we are taking 100 cm cube conical flask. Look, as you can see, 250 cm cube, the solution will be more spread out. It's not a, no, the volume is the same. This 250 cm cube means the maximum volume which it can hold. 100 cm cube conical flask means maximum volume which it can hold. But we have, in both cases, we have a solution of 60 cm cube, because that is the amount of the solution we have. So what happened? The text will disappear in a short time in 100 cm cube flask is not about the rate or the speed of the reaction. It is the depth of the precipitate, because 100 in a 100 cm cube conical flask, the precipitate will have a greater depth, whereas in 250 cm cube conical flask it will have a smaller depth. So it's not about rate, it's not about the total volume. When you compare, you will compare the depth of the solution. So in 100, so it will take less time for the text to disappear, because the 100 cm cube flask, the depth is greater. In both reactions, you have 60 cm cube of the mixture in both of these flasks, conical flasks. One, you was using a 250 cm cube conical flask, means the maximum volume it can hold, and another one you are using 100 cm cube conical flask. So when the reaction will occur, the depth of this precipitate will be greater in 100 cm cube conical flask as compared to that in 250 cm cube conical flask. So you can see the text for a longer period of a time, because small thickness, here the text will disappear in a short time because of greater thickness or greater depth of solution or height of the precipitate. Is it clear? Sketch on a grid the graph you would expect if all experiments were repeated at a lower temperature. So example, if this was your initial graph, so it will take more time, so same shape of the graph will be identical. Like this was your first graph, so the shape of the graph, it will be the same, and it will take longer time. As the reaction rate will be slower, so shapes will be same, but it will be above the original graph. Two solutions A and B were analyzed. Tests on solution A, some of the tests and observation are shown. Tests on solution A. Solution A was divided into 3 equal portions. The pH of the first portion was measured, so pH is 1. It shows that it is a strong acid. Less than 7 shows acid, and 1 and 2 shows strong acid. Test 2, magnesium ribbon was added. So magnesium ribbon means metal. So when metal is added to acid, It will give metal react with acid, give salt and hydrogen. That's why effervescence means rapid formation of the gas. Continuously a gas is given off. And lighted splint pop, it means hydrogen gas is released. Dilute nitric acid followed by barium nitrate, white precipitate. So that is a test for sulfate ion. So if this is giving a positive test, which acid is this? So it is a sulfuric acid, because sulfuric acid contain a sulfate ion. Identify the gas produced in test 2. Which gas is produced in test 2? Hydrogen. Identify the solution A. What is solution A? That is sulfuric acid. Test on solid B. Another solid is there and we are testing the solid. Solid B was zinc carbonate. So they give you the identity of the salt, that is zinc carbonate. Complete the expected observation. Dilute nitric acid was added to solution B. We add an acid to a salt of carbonate. The gas produced was tested. What we'll observe? First we'll observe fizz or bubbles, effervescence, and the tested with the lime water. Which will turn milky or cloudy. The second one, zinc nitrate solution was formed, is divided into two portions. Drop of sodium hydroxide. When we have a zinc salt and we are adding sodium hydroxide, what is the observation of adding a sodium hydroxide to a zinc salt? So it will give white PPT. And the second part, drops of aqueous ammonia is added. Sorry, excess of sodium hydroxide is added. What is the observation? Zinc precipitate are white, and when you add an excess, so precipitate dissolve and it will form a color or colorless solution or a clear solution. White PPT, which will dissolve to form a clear solution or colorless solution. Drop of aqueous ammonia is added. What is the observation when we add aqueous ammonia? Again, white PPT. One mark is for mentioning this white, the color. And in excess, what happened? When we add, so precipitate will dissolve. Again, the precipitate dissolve and form a colorless solution. Zinc precipitate are soluble in both aqueous ammonia as well as aqueous sodium hydroxide. Okay, this is the planning of experiment, the last question. Potassium chloride is a salt that dissolves in water. The solubility of the salt is the mass present in a gram in 1000 cm cube of water at a particular temperature. Plan an investigation to determine the solubility of sodium chloride in 40 cm at 40 degrees centigrade. You're provided with potassium chloride, the common lab apparatus. So how we can plan this experiment? Basically, what we want to do, we want to find how much potassium chloride dissolve in 100 cm cube of distilled water at 40 degrees centigrade. That is the plan. So we'll use a water bath and we'll keep a temperature. So first, it's better you mention, that's right, water bath is there. First, you will take a flask or a container or a beaker. So first what we'll do, we'll take 100 cm cube of distilled water. By the help of, because you should mention the apparatus as well in this planning of the experiment. So we take 100 cm cube of distilled water by measuring cylinder. Reason why I did not mention the burette here, because burette can measure maximum 50 cm cube. So I have to refill the burette and transfer to a beaker. That is one thing. Then we want to maintain a temperature. We want to keep the temperature same. Even you can use a thermometer to make sure that it is placed thermometer. Then heat to 40 degrees centigrade. And maintain a temperature. By help of water bath, so that it will maintain the temperature. Then we will add potassium chloride until no more dissolve. And how we can add potassium chloride, the solid, by help of spatula until no more solid dissolve. Then we will filter. But what we want how much mass is added. So how we can know how much mass will be added? Yes, you can mention until the solution is saturated or until excess of potassium chloride is added. Filter to remove excess potassium chloride. Yes, soluble salts are aqueous. It means when you add a salt to water, it will dissolve. That's why we call it aqueous solution. But these salt, it's not like all the salt. There is a limit to which a liquid can dissolve a salt. Like 2 grams, 5 grams, 30 grams, and it changes with temperature, because higher temperature, more space available between the particles, so it can dissolve more. So filter to remove excess of potassium chloride, and then after removing, like filtering to remove the excess of potassium chloride, what we will do, because we want to find how much salt is dissolved now, so we will heat the salt solution to dryness. Heat the salt solution to dryness means until like no more water is left, and then we will measure the mass of solid left by help of balance, and then use formula. What formula you'll use? Mass of salt divided by volume of solvent to find concentration, sorry, to find solubility of solution at particular temperature. So your experiment should have all details. Your experiment should have all details of the apparatus which you are using and the steps you are carrying out and how you are carrying out those steps. No need for repeat. This is a experiment will take longer time. It's not repetition is for experimental accuracy. You can do repeat the experiment, but when you want to evaporate 100 cm cube of water, it will take or a salt solution. It will take lot of time. Yeah, that's right, Mohsen. Already, because in this one we took 100 cm cube of the water. So in place of volume of the solvent, I should write directly 100. Is it clear? Any question related to this paper? So I want everyone to solve this now and submit this paper. It's not necessary just after the class. You can take time in evening. You can submit this, but try to submit today. May June 2018, paper 6, variant 1.